Hello and welcome to our final capstone presentation. We are Team 26045, the Automated Weight-Bearing Ultrasound Foot Scanner. We are sponsored by the University of Arizona Biomedical Engineering Department, Dr. Russell Whitty, and Dr. Daniel Latt with our mentor M. Cecilia Luria Gosler. This project represents our interdisciplinary efforts to give clinicians a simple, automated solution for assessing the stiffness of their patients' arches. In this presentation, you'll see our design process development, milestones, and demonstrations of our final project.
Hi, I'm Shay Ivy, the team lead, and I'm a biomedical engineer.
Ariana Gibbs, and I'm the procurement lead, and I'm also a biomedical engineer.
Hello, my name is Justin Lee, and I am the signal processing lead, and I am an optical engineer.
Hi, I'm Ruth Salazar. I'm the mechanical lead, and I'm a biomedical engineer.
Hi, my name is Tanisha Tariq. I'm the software lead and I'm a software engineer.
Hi, I'm Emma. I'm the biomechanical lead and I'm a biomedical engineer.
So why does this matter? Our system is used to diagnose progressive collapse of foot deformity, which is a condition that affects around 10% of adults over the age of 65. Current systems like X-rays and CT scans are able to capture the foot under natural weight-bearing conditions, and while ultrasound is more safe and accessible, it's not typically repeatable or automated in this way. Our system aims to combine our weight-bearing conditions with automated scanning for more repeatable, clinically useful data.
In the beginning of the year, we had set parameters for our system requirements that Parent Foot Scanner needs to accomplish. The first being performing automated ultrasound scans of our plantar foot, and then maintaining the motor step size, scan distance, and probe rotations. With those certain distances, we would then synchronize that with our ultrasound data acquisition, and from there we would get our 3D reconstruction and analysis of the time-frame fracture info.
When we received the project, previous teams had already built a strong mechanical foundation for us to build upon. They created a metal frame structure that included a weight distribution system, and the motors beneath the platform had movement in one axis. However, their system had limitations. For starters, the motors were not fully integrated into the code, motion imaging were not synchronized, movement was in one axis, and their GUI did not allow for an automated scan. So our job was to take this partial system and convert it into a fully functional prototype.
A major part of our work focused on improving the mechanical design. First, we redesigned the motor mounting system. The previous PLA bracket was bending and causing stability issues, so we redesigned it, improved the fastening mechanism, and printed it using a stronger filament, PETG carbon fiber. We also redesigned the heel cup to stabilize the patient's foot during scanning and allow imaging of the entire desired soft tissues. Finally, we added a third motor to allow a 90-degree rotation of the ultrasound probe and designed a mount for said motor and for the ultrasound probe.
We updated the power system to handle higher voltages and currents for our given requirements. These involved stepper drivers for each of the motors, limit switches for calibration and homing. We also had on and off switches, as well as an emergency stop for safety, and we upgraded our power supply from 18 volts to 24 volts.
We also addressed wiring challenges by introducing terminal blocks and adapters to safely distribute power throughout the system. All these improvements helped us to control each motion component of our system.
One of the biggest issues that we faced was software integration. Initially, we had the motor script and the imaging script as two separate things, and even with the imaging script, there was two separate variations of that. To fix this issue, we had to integrate the motor logic into the scanning logic. We implemented this motor control logic in both the B-mode scan and the shoe-wave imaging scan, and also it allows the users to adjust the scan distance and the step size for both these modes. By integrating the motor controls directly into the Verisonics image capturing script, we were able to do a step and capture method of getting our data from the ultrasound scans. What you're seeing here is a full scan of the system in action. The probe moves incrementally across the foot while capturing ultrasound frames at each step. This step and capture method ensures consistent spacing between images, which is critical for future 3D reconstruction. As the scan progresses, we are able to visualize internal structures of the foot, which can eventually be used to assess tissue properties and structural integrity.
We faced many challenges throughout the project. Mechanically, simply accessing the frame was complicated. We had our frame stored in one lab and the ultrasound system stored in another, so getting the entire system together to begin testing required some extra coordination and time to begin with. Electrically, we ran into wiring issues very early on. The wires that connect to the motor coils were switched up, which caused our motors to not always move consistently. To fix this, we had to trace and reconfigure the wiring to get the motors to move consistently and reliably. On the software side, getting the motors to work with the ultrasound system was a major hurdle, as they worked independently initially. Overcoming these challenges required a lot of troubleshooting and coordination across all mechanical, electrical, and software components, but it ultimately allowed us to build a reliable system.
While we made significant improvements, there are still areas for future development for next year's team. The first improvement would be improving the system's portability. The system is very large, and our mentor stressed the fact that we want the device to be able to be easily moved around to different areas. Another would be improving the scan parameters for overall better image quality, and then finally exploring different probe options. Together, these improvements would overall help move the system closer to being clinically applicable. The results demonstrate that we successfully achieved fully automated ultrasound scanning. The system is able to control probe movement, synchronize imaging, and complete a full scan without manual intervention. We also confirmed that scan data can be reliably captured and saved, allowing the users to store and retrieve data sets. Overall, this shows that our system functions as an integrated end-to-end scanning platform. To verify performance, we conducted several verification tests. We confirmed motor step size accuracy within plus or minus 0.2 millimeters over a 100 millimeter range. We also confirmed motor rotation accuracy within plus or minus 3 degrees. In this sped up video, you can see real-time images displayed on the user interface on the left, while an ultrasound scan is occurring on the right. This passed our verification test of the user interface displaying real-time 2D ultrasound images during scanning. Although we are still waiting to complete some of our verification tests, our current results demonstrate that our project is on track for fulfilling all of our system requirements.
In summary, we successfully transformed a partially developed system into an integrated, automated ultrasound scanning platform. Our work lays the foundation for future teams to build on and continue advancing this technology. Thank you for watching.